Okay guys, welcome to this vodcast on the first part, the take-home part to the application SAC 2019. Okay guys, this question was done pretty well. It was designed to be a straightforward, comfortable lead into this part of the SAC. You've got to show that locus of complex numbers describes a circle centered at 4, 4 with a radius of 6. So the way to go forward is to generalize Z in Cartesian form, x plus iy, and aim to get a Cartesian rule of the form x minus 4 all squared plus y minus 4 all squared equals 36, the square of 6. So there it is. You can see I'm making that replacement, and I'm also appealing to a property of modulus, where I'm able to separate it as mod numerator over mod denominator. So separate the entire mod and multiply mod denominator across. First step. Okay, then I'm collecting my reals, collecting my imaginaries, and then of course appealing to the definition of mod, which is real squared plus imaginary squared square root. That's an important step. And then of course it's all about squaring, collecting terms, and so on and so forth. So it's a bit of a drudge, but it's a common problem and it's important to revisit it. So there it is, expanding the brackets, collecting all your like terms. You'll get down to a point like that, completing the square, 2 lots of 16 I add to both sides, and voila, there you have it. Okay, part B, find the Cartesian equation for the locus of complex numbers that satisfies that condition. Okay, hopefully most of you are onto it. It's of the form mod z minus a complex number equals mod z of another complex number. As we know, this turns out to be the perpendicular bisector between the 2 points involved. So think of those Cartesian, those complex numbers in Cartesian form as a pair of points. So obviously we're dealing with the coordinate point 4, 4 and 10, 10. The midpoint is of course 7, 7. The gradient between those 2 points will be positive 1, so the perpendicular bisector will have a gradient of -1. Whacking it into the linear equation finder, we come up with our rule. A fairly simple problem, I would hope. Okay, part C, find the area of the region enclosed by the 2 loci described in part A and part B. Now, a lot of you correctly question this. Is it the minor segment or the major segment that is being asked for? And I clarified that it was in fact the minor segment. And once you got that instruction, you're good to go. So how do you go about finding the points of intersection between the straight line y equals 14 minus x and the circle? Of course, wherever we see y in the rule for the circle, we replace it by 14 minus x. I've done it by hand, but it's easy enough to just whack that into a calculator as the simultaneous equations even. Okay, you get x equals 4 or 10, and y obviously is 14 less that, which gives you to the converse, 10 and 4. So the points of intersection are 4, 10, okay, which obviously rises 6 above the center of the circle at 6, 6, and 10, 4, which is 6 to the right of the center of the circle. So interestingly enough, it's easy to realize each of those points, the angle subtended by the chord connecting those 2 points at the center will be 90 degrees. Easy enough to work out, I would think. So calculating the minor segment is pretty straightforward. It's a quarter circle of radius 6 minus the area of the triangle of height and base equal to 6, and that leads you to your answer. So be prepared for those sort of questions in your exam. Okay, question 2a. Show that a general solution for all points of intersection between the graphs of y equals sec x and y equals sec 2x can be written in that form. What important piece of information is missing? What the hell is k all about? Of course, you guys made the correct assumption. K was an element of the integers. That really did need to be stated in the question. However, let's proceed. Okay, so we've got sec, we're equating the 2 rules. Sec x is equal to sec 2x. Lo and behold, it drops out to cos 2x is equal to cos x, naturally. A simple application of the double angle rule for cos leads us to a hidden quadratic. Okay, so we then go and solve that as a quadratic. There we go. So it leads us to two solutions, cos x equals minus a half and cos x equals 1. You got half the marks available to you at that stage. However, we're not solving for cos x, we're solving for x, and there's your an approach to a general solution. Two particular solutions in a cycle, 2 pi and 3 minus 2 and pi and 3 for one equation, x equals 0 for the other, and then we add k lots of the period to each of those to get our general solution. Okay, 3 marks out of 4. The last mark is realizing that 1 on cos, any even multiple of pi, cos will give you 1, so that's why the y coordinate of 2k pi was equal to 1, and then subbing either 2 pi on 3 or minus 2 pi on 3 plus even multiples of pi, that's obviously not adding anything to the value, will give us 1 divided by negative a half, which turns out to be minus 2. So some sort of statement as to where the y values were coming from was required for the final mark. Okay, so here are the graphs. There's 3 marks. I haven't put a marking scheme on here. Okay, so you've got the 4 asymptotes for y equals sec x. X equals minus 3 pi and 2, minus pi and 2, positive pi and 2, positive 3 pi and 2. And then you've got doubly as many for sec 2x that you can see below. All right, so I guess I'd give 1 mark for the correct asymptotes, 1 mark for the correct shape, and 1 mark for showing that the two graphs are really crossing down there at x equals 1. In fact, in this case, there's only one point of intersection, at x equals 0, at 0, 1. And all the other ones for negative y values should be crossing at the grid line corresponding to y equals minus 2. So I was really looking for that. If you were somewhat off, I would be a bit lenient, but that was the general shape I was after. Of course, I would need to see the endpoints because that's explicitly in the question. So 3 pi and 2 minus 1 and 3 pi and 2, minus 3 pi and 2 minus 1 and positive 3 pi and 2 minus 1 would be the two endpoints that you'd need to label. And obviously they correspond to the sec 2x graph. Question 3, show that the vector OA is parallel to the vector OB. Guys, this is all that's required. The number of times I see overcomplication of these questions saddens me. All you need to show is that one is a multiple of the other. In fact, in this case, the multiple is minus 1. So OA is minus 1 times OB. That's enough to give you parallelness. So OA must be parallel to OB. Because there is a constant such that OA is equal to that constant times OB. Done. Very simple. State why this implies O is the midpoint of AB. Well, let's have a think about that. Of course, because O is a common point, we know OAB are collinear, and because OA is equal to minus OB, the length of OA and OB are the same. And because OA is equal to minus OB, OB is in the opposite direction of OA, you put all of that together and you have O being the midpoint of AB. Okay, part C, show that OC is perpendicular to AB. There's your classic dot product equals 0, an expression for AB, an expression for OC, and voila, it's as simple as that. Okay, this is really all I was looking for. I know some of you went into a justification of congruent triangles, AOC and BOC, etc. But I was just after the fact that any triangle of the form you see, if it has those properties to it, any triangle will have those properties if and only if it is in fact an isosceles. In fact, proving a triangle has those properties is equivalent to proving it is isosceles. So that's all I was looking for there, but of course I'll be a bit lenient because it wasn't entirely clear maybe what was expected of you. Okay, on to part E, a fourth point. So we're going into 3 dimensions now. XYZ is added such that ADC, BCD, and BCD are all congruent. So you've got 3 identical isosceles faces to this triangular pyramid, and of course, because they're all identical, the length of the base of each of those isosceles triangles are the same. So effectively, you've got 3 faces that are identical isosceles triangles and a 4th face that makes up an equilateral triangle. Okay, makes sense, doesn't it? But of course, the diagram makes it dead clear. So you didn't even need to infer that ADB was indeed an equilateral triangle. But you needed to draw on that fact in the dot product relationship, okay? Because firstly, that you'd calculated AD and AB as IJK position vectors, and of course you just multiply their I, J, and K together, but you're going to link that to the geometric understanding of the dot product as cos of the angle between them at A times the length of AD times the length of AB. Okay, now it's important to note, so obviously it leads to this expression over here. Now it's important to note, of course, that, well, cos, it's an exact value, but AB and AD side lengths of an equilateral triangle, so they, even though you can't directly work out AD, you do know it has the same length as AB and therefore is equal to 6. So putting all of that together, you've got the dot product of multiple expansions of IJ and K on the left. You've got the geometric understanding on the right. They match up. 18 is eliminated left and right, and you're left with just minus 2x plus 4y minus 4z on the left, which can be transposed to make x the subject as required. Okay, part F. State 3 other equations involving x, y, and z that result from considerations of length. Bit of a hint. Okay, so what we want to do is talk about CD. So CD would be D minus C. So the equations that you get. But what will be the length of CD? Of course, it'll be equivalent to the length of AC, which is equivalent to the length of CB. So let's just focus on AC. So there would be the expression for AC. OC minus OA gives you that expression. Its magnitude, pretty quick to work out. 1 squared, 2 root 2 plus 2 squared, plus 2 root 2 minus 2 all squared, square root leads you to 5. So that's a nice, neat little number. So therefore, CD, which has the expression you see below you, must have a magnitude of 5, leading to the first equation in that list of 3. Okay, so that's focusing on CD. Okay, now the other 2 considerations of length is AD, which we know is equal to 6, as well as BD, and it's just coming up with the Cartesian expression. So AD, X, so X, I, Y, J plus ZK minus your position vector for A, and similarly for BD. So there's equations 2 and 3 coming from side lengths AD and BD, and equation 1 coming from consideration of length CD. Okay, hopefully that's all clear enough. Okay, so solving any 3 out of the 4 above equations would lead you to that particular point for D. So a bit messy as it is, but there it is. So, and of course that's how I got it. I used 3 of those equations and I got myself values for X, Y, and Z that way. What we need to do in part GI is state a unit vector perpendicular to the face ABC. So in other words, the face ABC, any vector along ABC, OA, OB, OC, AB, BC, BA, any such vector is going to be coplanar along that face. Okay. So what we're going to do is talk about some general position vector. Call it U, and I'm going to give it the labels AI plus BJ plus CK, not XI plus YJ plus ZK, because that's already been taken in this question. So I'm using A, B's, and C's. All right, now, if I'm proposing it's going to, okay, so what I'm going to do is choose any two non-parallel options that lie on the plane ABC. And as you'll see, if I'll just click over that, I'm going to work with OA and OC. I'm not going to work with OA and OB. That's not going to get me very far because they're parallel, but choose any two that are non-parallel. So the general vector OA, or U times OA gives you that relationship between A, B, and C. I do U with OC, and interestingly enough, I get the relationship C is equal to minus B. Now that's all you really need. So this doesn't even need to be done with a CAS. So what that means is I can replace C with minus B in the above expression, and I have a link between A and B. So C will be minus B, A will be equal to 4B. That means any vector that runs perpendicular to the face ABC will have that general form. You can replace with B with anything you like. Okay, but let's make our lives simple. Let's just work with nice simple integers, and let's just work with B equals 1, and we have a vector that runs perpendicular to the face ABC, and then we're going to convert that to a unit vector by dividing through by its magnitude. And there it is. So there's a unit vector perpendicular to the face ABC. And of course, you could have actually had the negative opposite of it. It's going to either rise above it or rise below it, would be one way to vaguely think about it. Okay, so this leads to a beautiful application of the scalar resolute. In fact, it's one of the loveliest. I used to work with a teacher, Miss Callahan, and this was one of her favorite types of questions. So basically, I'm going to take any vector from the base to the vertex. I could choose an edge of the pyramid. This time I'm just going for as simple as possible. I've just gone for OD. So there's a vector from the base to the vertex. And I'm looking for the scalar resolute of that vector in the direction of my perpendicular vector. And of course, the scalar resolute, I'm not after a vector, I'm just after a magnitude after all. And by a use of your CAS calculator, if I take OD, so using the coordinates given, multiply it, dot product with vector U hat, as we determined before, you end up with that particular value. Very handy, powerful technique to remember. Okay, so what is formula for the volume of a pyramid? 1/3 area of base times height. As it turns out, you're dealing with nice numbers therein. So area of ABC, 12. Volume 1/3 times 12 times 3 root 9 on 4. Leaves you with a nice little answer of 3 times root 39. I just thought I'd share with you an alternative that lies in this particular case of isosceles faces meeting together. So if I take CO, I know CO runs, so the ABC meets the angle that the face ABC meets with the face ADB can be determined by the line that runs through those faces perpendicular to each other. So this ability enables me to think of an alternative way to go. So, and that's of course particular with these ideas that we're working with isosceles faces. So CX, so if X is a point directly below D on the face ABC, I could think of the distance from the vertex C to X along the face ABC to be the scalar resolute of CD in the direction of CO. So I can just perform a quick calculation through the rule. Okay, ugly old numbers I know, but you're left with quite simple answer of 7 on 4, 7 quarters. So using Pythagoras, okay, we know length CD is 5. I can work out the height in that particular way. So that's just interesting. And once you know the height, then it's the same sort of calculation for the volume of the pyramid. All right, this was quite a nice little algebraic test, I think, and a test of your understanding at the same time. So firstly, we have to work out the rate of change of x with respect to y, differentiate x with respect to y, and there was just a simple chain rule and an application of inverse sine, common base, so I can add them together. Nice and neat. Okay, I need to find the double derivative of y with respect to x. The first thing I do is I take my previous answer and reciprocate it. Now understand what the double derivative of y with respect is. It's the derivative of dy dx with respect to x. So I can't, it would be incorrect if those of you who took dx dy differentiated x with respect to y a second time and reciprocated it, that would lead to an incorrect answer. And this question was deliberately put in place to exploit that maybe misunderstanding you may have had. So I can't say the double derivative of y with respect to x is equal to the reciprocal of the double derivative of x with respect to y. We did have that lesson in class, but I think it needed further emphasis. So how do you take that expression for dy dx and differentiate it with respect to x? Well, it's implicit diff, isn't it? So that's what we're doing. We're implicitly treating y as a function of x. So this is the first step involved in that. So it's the quotient rule. Derivative of the numerator, which we've already calculated above. So it's minus y on the square root of 1 minus y squared. Now it's implicit diff. That's the outer rule. The inner rule is y. So dy dx times by the denominator function minus our numerator function times by the derivative of our denominator function. So outer function 1 minus y. So differentiating that becomes minus 1 times by dy dx. Okay, so that's all over, of course, the denominator function squared. Okay, so that was the important first step. Okay, if you could get over that hurdle, I think you're good as gold. You factor it out. So you factor it out. So our first term is minus y times 1 minus y. Our second term is has that as the numerator over the square root of 1 minus y squared. The second term is positive plus the square root of 1 minus y squared. All of that's being divided by the denominator squared. Where to from there? I've already got dy dx. So that first expression you replace with dy dx. Okay. Okay, I had some simplification going on first, but when I do perform that simplification and then replace dy dx with the square root of 1 minus x squared over 1 minus y, I get some other nice cancelling, leading to the nice, neat, simple expression. This double derivative of y with respect to x is 1 over 1 minus y squared. Very good. Okay. I wonder if there's further information. Yes, there was another part to it. The final part was, for the graph of this relation, identify its concavity and state the number of points of inflection. Okay, so since the double derivative is never zero, there are no points of inflection. And since it's determined by y values rather than x values, since that's never negative, it's always concave up. Of course, it is undefined at y equals 1, so that might, but that's just the very end point of the function itself, but it is concave up everywhere. And finally, on to 5. Question 5 was a bit of a monster question, a big test of geometric thinking, and really it was motivated by a mashing of two similar-ish questions. Well, the second component was quite similar indeed in the extended response part of your Chapter 3 review. Doing those chapter review questions are very is definitely worthwhile, people. So get onto it. All right. So okay. So there's the diagram. Kind of says it all. Show that the radius of the circle is the reciprocal of sine theta. So let's just focus on triangle OBC. Of course, it being isosceles means we can split it into a right angle triangle, radius r and opposite length 1, and leads you to the radius being 1 on sine theta or cosec theta. Okay, the second part was getting an expression for Q. The first thing is, okay, of course, it's also OAE is also isosceles, which I can split into 2 equal right angle triangles. So the angle is 360 or 2 pi minus the sum of theta, 2 theta, 3 theta, and 4 theta, which is 10 theta. All divided by 2. The angle in there is 180 minus 5 theta, or pi minus 5 theta in radians. And opposite length is obviously Q on 2, and we've already determined the radius to be 1 on sine theta. And then it's just your good old SOHCAHTOA. Good old SOHCAHTOA, but of course sine pi minus 5 theta is just sine 5 theta. So just working with that property of sine, an important property indeed, leading you to Q. Okay, these parts really don't need much explanation. Simple application of the quotient rule again. Okay, just collecting some like terms. So I needed to see some sort of application of the cosine rule. And Q dash is 0, we can just focus on the numerator, setting that equal to 0, moving terms to the other side of the equation, dividing through by cos theta, dividing through by cos 5 theta, and we can put it into the tan theta via the ratio. Tan is the ratio of sine to cos. Okay, explain why the least upper bound on theta is pi on 5. Okay, so if it's ABC, DE is to remain a pentagon, that means points E and A must be distinct from each other, must be separate. And of course, if the sum of the all angles made up of the 4 existing triangles, the first 4 triangles, equals 360 or 2 pi, we're at an angle of pi on 5. So obviously that is the absolute upper bound if we're to maintain ABCDE has existence as a pentagon, a cyclic pentagon with all vertices on the circle. Okay, now differentiating that with your CAS leads you to that expression for Q dash. It's in fact minus 16 sine 4 theta minus 8 sine 2 theta. So with that form of the equation, it's quite easy to see that Q dash will in fact always be negative for any value of theta over the given domain from pi on 12 up to but not including pi on 5. Why would that be? Because if I take 4 pi, the lower bound will be pi on 3, the upper bound will be 4 pi on 5. 4 pi, so 4/5 of pi is less than pi, less than 180. That's the largest possible value you'll get. Sine is always going to be positive throughout that domain, therefore. So 4 pi and 5 is still in the second quadrant. Sine is positive in that second quadrant. Therefore, sine 4 theta and sine 2 theta over that domain will always be positive. They're both being multiplied by negative values. That means Q dash must always therefore be negative over that domain. So it was that simple. So it's a decreasing function. Now that leads directly into the way into part G. Use the compound angle rule to find the largest value of Q. If it's consistently decreasing over that interval, Q is a function of theta, then the largest value of Q must occur at the first endpoint, at the least value in the domain, so at the lower bound of the domain. So in other words, really, this is coming down to evaluate Q when theta is equal to pi on 12. So that statement needed to be made for full marks. Oops. Okay. I'm not sure why that covered up, but there you go. Okay, so that's what it's about. So find Q, the value of Q when theta is equal to pi on 12. So I wanted you to work with your compound angle rules. So there's sine 5 pi on 12 is involved, is the numerator. Sine pi on 12 is the denominator. Now you don't need to do further calculations once you've performed all of that. Okay, and then of course, what is Q? It's 2 times sine 5 theta over sine theta. So I just wanted to see some nice cancellations going on, and then a bit of rationalizing the denominator to finish it off, and it led you to 4 plus 2 root 3 as your answer. Okay, all good. All right, H, state the value of theta for which the area of cod is equal to the area of DOE. So adjacent triangles subtended at the center using edges of the pentagon. Now, of course, what I was hoping you would do is realize, well, what's the area of a triangle? Half BC sine A, because we're dealing with the radius in both cases. Really, COD will be the same area as DOE when sine of 3 theta is equal to sine of 4 theta. Now you can whack that into your CAS, but if you think about it, it actually drops out quite nicely. So 3 theta and 4 theta are both angles less than 180. Okay, so we're both talking about positive sine. So when will two angles between 0 and 180 have the same evaluation of sine? Well, it's got to be via the complementary property of sine. Sine pi minus that angle is equal to that angle. We can apply it, so 4 theta being the larger angle, pi minus 4 theta must have the same value as 3 theta. Just thinking about your complementary, not complementary properties, your symmetry properties, I should say. Don't want to confuse it with symmetry about the y. So there it is. So solving that very simple linear equation leads you to pi on 7. So that's potentially a tech-free question, which is quite neat. Show that AB, the length of AB, is equal to sec theta on 2. Let's just call AB x, and of course, it yet again being an isosceles triangle, we can split it equal to 2. The angle in there will be therefore theta on 2. We know the radius is 1 on sine theta, and then we go through the process of sine theta on 2 is x on 2, the opposite length divided by or times by sine theta in the end. Let's make x the subject as follows. So it leads you to that expression, 2 sine theta on 2 over sine theta. That's not the required expression, however. So what we're going to do is use a double angle rule to convert sine theta into 2 sine theta on 2 cos theta on 2. Why are we doing that? Because that's where we need to go in this question. We get a nice cancelling and we're left with a lovely sec theta on 2 answer. You may have come up with it via other means, and that would be perfectly fine so long as they are valid. Okay, there was a lot of work for this for 1 mark. I should have made it 2 marks, but anyway, here it is. All right, so this would be the line of reasoning. So firstly, we know OBA is isosceles, so the angle at A and B, well, the angle at A is 72 degrees, OBA is also 72 degrees. Now we know ABX is also isosceles, so the angle BXA must be the same as the angle BAX, which is 72 degrees. So we can work out the angle XBA, the vertex of that isosceles triangle, to be 36 degrees. Okay. If that's 36 degrees, if XBA is 36 degrees and OBA is 72 degrees, it means OBX must be also 36 degrees. Aha! Let's focus on triangle OBX. 2 angles of 36 degrees, we're dealing with an isosceles triangle, therefore OX is equal to BX. That's it. Okay, lots of right angle triangles throughout this task, wasn't there? So now we're going to focus on BMX. It's an isosceles triangle, so we're going to split that 36 degree angle at B into 2, 18 degrees. So we need to find MX. Let's just label it X. Now we were told that BA was sec. Well, from a previous result, it would be sec theta on 2. In this case, theta is 36 degrees, so we know BX must be 1 on, well, it must be sec cos 18 degrees, 18 being half of 36. Okay, with that in mind, off we go, and we use our sine rule. So sine of 18, opposite on adjacent, leading us to our length x as being sine 18 over cos 18, which is equal to tan 18. Pretty okay, I think. Okay, BMO consists of length OX, which we know to be sec 18, so sec theta on 2, and theta is 36, so sec 18, plus our tan 18. Now I'm just going to write tan 18 is sine 18 on cos 18 because we have that common denominator, which simplifies the answer as follows. Now OB is the radius of the circle, and and the radius of the circle is equal to 1 on sine theta, and theta is equal to 36, so the radius of the circle is 1 on sine 36. Pulling it all together now, so we're going to apply cos of 36, which is MO over BO, and we get a nice expression, as you can see. But of course, sine 36 is not in the expression for cos 36, so we need to use a double angle rule, and then we get a nice cancelling. The cos 18s will disappear, and we're left with that expression for cos 36. Okay, last but not least, we need to show that that hidden quadratic emerges. So clearly it's just an application double angle rule for cos, linking cos to sine in the way we've seen before. So with that replacement, cos 36 goes out, in comes 1 minus 2 sine squared 18. We collect some like terms, and we get the quadratic as desired. How do we neatly solve a quadratic? Well, always via the quadratic formula, unless it factorizes neatly. And we're left with that sine 18 equals minus b plus or minus b squared minus 4ac. With a bit of simplification, we can see it comes down to minus 1 plus or minus root 5 on 4. But of course, it's not ambiguous. We type sine 18 into our calculators, we get a singular answer, and 18 degrees is in the first quadrant, so sine of 18 must be positive. We reject the negative, and we come up, the 4's been chopped off, and we come up with our correct answer, minus 1 plus root 5 on 4. And that, folks, as they say in the classics, is all. So thanks for listening. Catch you next time.